All right. So today's lesson is from section 12.2. It's a follow of 12.1. Okay, we're on the same topic still. Now what we're going to do, though, is we're going to measure simple harmonic motion. Okay, measure simple harmonic. Maybe it'll help. Okay, I saw you doing this. That's right. We're going to measure simple harmonic motion. So, two objectives. First, we want to be able to identify the parameters. Remember, what is parameters? Ooh, parameters. We talked about this on one of our tests. I told you because it was a question. It said, what parameters affect the momentum of an object? And the answer was mass and velocity.
Yeah. It's like what units or what variables. Yeah.
Variables, good. It's like what variables, okay? It's another word for variables. You're going to hear it a lot, okay? Parameters. Identify the parameters that describe simple harmonic motion. So we're going to talk about amplitude, period, frequency, wavelength, all that stuff that we started talking about yesterday, okay? Second, we're going to calculate the period and frequency of an object in simple harmonic motion, okay? And I showed you guys that graph yesterday of that sine wave, okay? That sine wave. It's going to come up again. Okay? It's going to come up again when we start looking at waves in general. So when we look at sound waves and optics, we're going to see those waves, okay? And we're going to talk about stuff there. For today, we're going to look at a few formulas that will help us. And again, you're going to be given these formulas. Please keep in mind that the formula like Fs equals negative Kx and the ones you're getting today are going to be added on to the ones you already know. Okay, so that formula list is getting longer and longer. So you need to know what is useful where. Does that make sense? Okay, you can't just say, oh, here's all the formulas. You got to know that Fs equals negative Kx is a spring. Okay? Helen.
Alright, so remember that thing we used when we were doing like the velocity times time graph?
Yeah, the velocity and time graph, the motion sensor.
The motion sensor?
Yes.
Is there any way you could use that and like pretend you're a spring like you were?
You actually can. Yeah.
I was actually thinking about that. Like you set it as like a certain spot. Then
you can. You're absolutely right. If you and you know what? If you had a motion sensor that had a calibration that was on a high enough scale, you could actually take a spring and let it go, and it would be able to measure the amplitude of the spring. Yeah, not just a person. But that's like one that would really, like, that would have to send out a pulse, like, you know, every millisecond, and a pulse in a certain range also to see. So it'd be a lot tougher, but it is possible. So you can measure the motion of it. And when I was in college at Villanova, in the labs, we had really good labs. That's one thing I loved about the school. Yeah. I had the jersey on.
Oh, yeah, we saw it.
I was like, what?
Villanova?
I don't know about that, but the labs were a lot of high-tech stuff. Like, we had the scanning electron microscope in there that was amazing. I mean, you could see like such crazy stuff, and like, you could see into different objects and see what's going on with the molecules and stuff. There was a lot of dynamic labs that were able to like.
Is it like X-ray vision?
No, but it's a scanning electron microscope. It sends like electrons into it and it gets a result.
The table that would show you like the microscope. Is that what you're saying?
No, that's different. I'm just saying there's different things there. But we had one that was.
We got off of that subject.
Yeah, it was off topic.
Okay.
But there was one lab. So you can write this while I'm talking, by the way. There was one lab that we actually did exactly what you're talking about, Helen. We used a mass spring system, and then eventually we turned it into what's called a mass spring damper system. And what it was able to do is it was a sensor that was able to actually measure and put a computer readout to show you the exact wave that it performed. It was really cool. And the minute you introduce the damper is the thing that makes it go, instead of this all the time, the damper adds friction. So it causes it to do this now. And you would see that. You could actually see the oscillations getting smaller and smaller.
Can you do it with no friction? Can you say that?
Yeah, so we set it with no friction also. And it's just a wave that goes on. And the only way you can do that is if you have a force that counters the friction that's inherent in the object. Because there's obviously friction no matter what. So you need some applied force or some external force.
Is that a W?
Yeah, so let me explain what these are. First, amplitude is capital A. I'll go through the definition. Period. This is, remember tau from yesterday? And I'll write it a little bit bigger. This is the symbol for period. Tau. It's like a capital T, but it's not, you know, in the...
It's like a script T.
Yeah, it's not in the Arabic language, okay? We write Arabic. This is not Arabic, this is Greek.
I write Arabic.
And then the last one is called omega.
Omega.
And it looks like a W.
Omega.
Now, let me make a quick point because some of you might get a little bit confused if you use the textbook and read. The book does not use omega for frequency. they use F. Okay, but it's omega. You're never going to use F again. It's always omega. I don't know why. Physics textbooks in high school use F. They think students can't handle, I guess, the symbol. They want to use F because F, frequency, it makes sense, right? But you're going to always see omega. Okay, if you go on to any other science, you'll see omega. And you'll talk about something called a natural frequency, which is omega n. But we're not even going to get to that, okay?
So
but omega.
W thing?
Yeah. Okay, but we're going to call it omega. I'm going to say omega, so get used to that, okay?
And frequency is measured in hertz?
Yeah, so Hertz, okay? Hertz is really, when you change your radio station?
Yes.
Have you ever looked at the units at the end?
No.
It's in megahertz. It's a frequency you're tuning into. Okay, MHZ, very good. Capital MHZ. Yeah, it's megahertz. That's what it is. It's hertz, but on a level of 10 to the 6. Okay, 10 to the 6. Kilos 10 to the third, megas 10 to the 6. So you're tuning into a frequency. That's why you change the frequency on the dial. It receives different radio waves at that point in time. Okay, so that's what frequency. Now, what a hertz, or what a hertz, I guess, there is no singular form, but what a hertz really would be.
Wait, why are I don't know, isn't there a chain of car stores called Hertz? Yeah.
Yeah.
Yellow and black.
I don't know why it's called hertz, actually. That's a good question.
Something with the vibration.
Yeah, probably has to do with that, yeah. Yeah.
Or it's someone's last name.
That's possible too, yeah. So, hertz really measures, okay, the amount of cycles per unit time. So, for example, if the spring did this, and watch my hand, if the spring oscillated once in 1 second, it would be 1 hertz. If it oscillated twice in 1 second, it would be 2 hertz. 3 times in 1 second, it would be 3 hertz. It's the number of cycles that occur per unit time. Traditionally, we use cycles per second. So a hertz, its units are really, hertz are really 1 over second. That's what a hertz really is, if you want to write that down. It's really 1 over second. Okay, and we'll see that in a minute where that comes from. And I'll show you where it comes from in a second. Okay, no pun intended, in a minute. So, amplitude, the units are going to vary. Yesterday when we talked about the velocity versus time, the velocity was on the y-axis, so the amplitude would have been meters per second. But if we look at position versus time, then the units would be meters along the y-axis. So amplitude is always going to change. The voice, or somebody's voice level, amplitude is measured in decibels. Okay, so amplitude, you're going to see units varying. But period, you're always going to see seconds. Well, not always, but in physics, you're going to see seconds in our formulas. And frequency, you're going to use 1 over seconds, which is defined as hertz, abbreviated capital H, lowercase z. All right? That's what we need to know what they are. Again, the period is the time it takes to complete the cycle. So if it takes 5 seconds to do this, then the period is 5 seconds. Okay? The amplitude is the maximum displacement. So remember, let's say that's the spring at rest. Okay? We're looking at the bottom now. That's the spring at rest there. And let's say that the spring is oscillating in simple harmonic motion, and when it comes out to be stretched, it looks like this. I'm going to use a red one, and I'm going to dash it. Okay? The amplitude is pretty much x. Remember x, the stretch length? That's what the amplitude is going to be. So the amplitude here would be measured from here to here.
Amplitude is the same as x.
Yep. Okay? And we're going to see that, yeah, for simple harmonic motion, it's easy to see that. But when we start talking about radio waves and light waves, we want to remember that amplitude is the actual, remember yesterday we drew that graph? The amplitude was the distance to the peak and the distance to the trough at the bottom. It was just that gap, okay? From the midline to the max and the midline to the min. That was the amplitude. It's the same thing as the x value with a spring mass system.
Why is it amplifier called an amplifier?
Because it increases or decreases the signal. Amplification, yeah.
What? So it's like the highest or the lowest?
Yeah, but it's not in pitch, but it's in sound level.
Yeah.
So like decibel level.
Decibels.
Yep. All right, those real quick before we get into any examples. All three are going to be given. You don't have to memorize, but we have to know what they're used for. Okay, we have to know what they're used for. So the first one is the relationship between period and frequency. The frequency is equal to 1 over the period. And let's take a look at this and make sense of it. The units of frequency, this omega on the left, if you remember the units, they are measured in Hertz. Okay, they are measured in Hertz. So this omega here is Hertz. And we can see that equals 1 over, what are the units of period again? Look at your notes from the last one we just wrote down. Seconds. So remember a minute ago I said a Hertz is 1 over seconds? That's where it comes from, right there. Those are our units to take a look at. Again, omega is measured in Hertz. Period is measured in seconds. So Hertz equals 1 over seconds. That's what we had a minute ago, and that's what I said to you guys. So if you ever have the frequency and you want to find the period, you can just use this formula. If you ever have the period and you want to find the frequency, same thing, but you can manipulate it as needed. What kind of a relationship is there between the period and the frequency? How are they related? What will we use? What term in math would we say when we see that something is in the denominator on one side and in the numerator on the other side? It's a reciprocal relationship or inversely related. Very good. I'm going to write inversely related, and let's write reciprocal, please. Now, remember the other day, and we talked in class, we talked about how F was proportional to X. When we talked about, well, when the spring stretches more, it's because there's more force. So the force was proportional to the spring being pulled. That was directly related or proportional. This is the opposite. And think about it for a second. If you plug in a number, somebody give me a number for the period in this problem. Any number. 3 and then 5. That's fine. I needed 2. So say we plug in a 3 for the period. Omega would be 1/3. Okay, if the period was 3, it'd be 1/3. Everybody agree with me? So if we take the period and increase it to 5, now omega becomes 1/5. What happened from 1/3 to 1/5?
As the period increases, the omega decreases.
Very good. That's exactly right. And that's what inversely related means. As the period of the oscillation increases, you can write this down in words if you want to give yourself a little bit of an explanation. As the period of oscillation increases, the frequency decreases. And again, that's what inversely related means. Okay? For those of you that are even somewhat interested in possibly taking the SAT physics, these kinds of questions are ones they put a lot on. Okay? A lot of emphasis on this stuff. The relationship between variables. So they might say, a force on a spring is exerted. If that force is increased, what happens to the displacement? Well, that also increases because those are directly related. So you need to know the logical relationship between the variables. You need to know that as the period increases from 3 to 5, the frequency is decreasing from 1/3 to 1/5. Okay? Again, the relationships are very key. And you'll see something like this on the multiple choice on your test, on your next one. All right, next. The next formula is the period of a mass spring system. The period of a mass spring system. Okay, so it's given as period equals 2 pi. 2 pi shows up a lot. Have you noticed that? Circumference is 2 pi r.
Yeah, why is that?
Because 2 pi represents, and you're going to learn about this. Have you learned about...
Probably not.
have you learned yet? You're going to, but... in Algebra 2, have you done anything with trig yet? Sine, cosine?
Our math class isn't exactly
Maybe?
stellar. No.
What about, have you heard about reference angles yet?
No.
Your last school or here? Okay. So you're going to learn about something called reference angles. And what you're going to hear is this. The full, what's the word? Circumference in what's called radians is 2 pi. That's why 2 pi shows up a lot. You're going to hear about 2 pi. 2 pi is really the measurement of a circle. 2 pi is the equivalent, mathematically, of 360 degrees. Okay? 2 pi occurs a lot. And if you remember from yesterday, we talked about a sine wave, right?
What's a 1 pi is equal to 180?
It's like half the sine wave. And 2 pi is the full sine wave. And think about it this way. Watch. This is not directly correct, but I'm trying to make you guys see what I'm talking about. If I had a sine wave like that, remember yesterday I drew this? If you take the bottom half and you superimpose it below that, don't you get a circle here? Okay? a sine wave is traditionally a period length of 2 pi. So you're going to see this 2 pi a lot. Okay, I'm just giving you a heads up for that. Anyway, the period of a mass spring is 2 pi times the square root of m over k. What's m? Mass. Mass. X is measured in meters. M is mass. K is what?
Stiffness.
Yeah, the spring stiffness or the spring constant. Okay? So, and let's think about this for a second. This is where we need to use logic, not just numbers and figures, okay? If I have a spring, and it's a really weak spring, and I let it go, it's going to go like this really fast, right? If I have a really strong spring, it's going to pull back, but what's going to happen is its oscillatory motion, okay, is going to be much different than if it's a weak spring. And think about that example yesterday. Remember, I showed that quick video where the spring was just oscillating up and down, and then there was another spring left and right? Okay, that was a very weak spring, and it was moving up and down. Whereas the other one was a very strong spring. So, looking at this problem here, if you increase the value of k, if k goes up, what's going to happen to tau, or the period in this problem? Think about how they're related to one another. Are they directly related? Are they inversely related? What's happening? Yeah. Let's look at it. If k goes up, I know, this is tough to see this sometimes. If k goes up, then you're dividing by a bigger number.
Oh, yeah.
If you have $5, and there's 2 people, Thomas and Sibyl, you split $5, you just get $2.50, right? But now, Hunter, Chelsea, and Caroline join the group. Everybody only gets $1, right? Because now you're dividing by 5 people. So when you divide by a higher number, the answer gets smaller. So if k increases, if the stiffness increases, the period's going to get smaller. Because what happens, think about it. If I have a really strong spring, when I let it go, it's going to quickly stop, right? That's a quick period. Whereas I have a very weak spring, and I let go, it's going to oscillate back and forth in some slower motion. And we're going to see more of this in the lab. And I'm tempted to even make you guys, or do the lab. We don't have class tomorrow, right? No, we have class on Friday and then lab here on Monday. I'm tempted to do the lab on Friday before we get into the next topic, so that we don't really forget what we're doing, because this stuff does make more sense. But then we'd have a double on Monday, a double lecture, which I didn't really want to do. So I'm going back and forth with it. But you'll see this in the lab, because what we're going to do is we're going to look at different springs, and those springs are going to have different stiffnesses, and you're going to measure the period it takes for it to oscillate up and down. You're going to measure the stretch. You're going to measure the K value using an actual spring scale. And this is a little bit more apparent when you do that. Okay? Now, the other thing to know is that the mass is directly related. So as the mass goes up, the period is going to go up. Okay? As the mass goes up, the period is going to go up. And make sense of that. Ready? You're hanging a mass from a spring. Say it's like I'm taking this pen and I'm hanging it from a spring and I let go. It's not really pulling down on it much, right? So the period might just be this little amplitude right here. It's not going to go very far. But if we have a very heavy mass, what's it going to do? It's going to cause the spring to go further down and further up. So it's going to take more time to do that. So if the mass is higher, the period is higher. If the K value is higher, though, the period is lower. Okay, so this again we see, this is directly related to tau. This is indirectly or inversely related to tau. Okay, and you can write that down. K is inversely related, the mass is directly related.
A pogo stick? Is that literally just a spring?
Yep.
So
It's a spring and oscillatory motion.
Is the equilibrium just when nothing's going on and just standing on it?
Yeah, and the thing about that is that your body weight is the force acting on the spring. Your weight itself is what is keeping that spring in oscillatory motion.
Wait, so I have if someone weighs more, then the pogo stick's gonna go closer to the ground. So does that mean that the maximum X or the maximum
amplitude is also greater? Yep.
So that depends on
the amplitude. We're not going to talk much about, but that will depend on the force also. Yep.
Because I thought yesterday we were saying this is kind of confusing because yesterday we were saying the maximum. I forgot what we were calling it. Maximum
amplitude.
No, I guess we were saying everything has a maximum, but that would if I went on a pogo stick and then a little kid went on a pogo stick, it would go more.
Yours the spring would stretch more, right? Because there's more force, so that increases the maximum amplitude.
So it could change.
Yeah, the amplitude changes based on the force that's being applied. Yep.
Okay. And what about it's kind of I thought of this when you said some springs don't really move. We like this park used to go to when we were little. There was one of those things like on an animal, like a
Yeah, and it went back like this.
No, it wouldn't move because it was the spring was so big, like it was so hard to get it to move. So like,
Yep, that's exactly right. I know exactly. You know what she's talking about right now? You go to the park. It's a little horse. It's not a seesaw, but it's a little like horse, and it's on a spring that's vertical. It's a vertical spring that's very, very rigid.
It was so hard to do.
Yep. But if two people got on, it could work, right? More force. More force, it can move more. There's more amplitude in it.
Little seat, I didn't try to get two people on one of those.
When you're a little kid, maybe. All right. Let's look at the next part. Take a look at this. Do we see the analogy here? Look at the formulas. Remember yesterday I talked about how a spring mass is the same thing as a pendulum, really? It's oscillating back and forth. But now, take a look. This is the most interesting thing. And I'm not going to derive it, but I'm going to just make a point of it. There's no mass in this equation, which is kind of crazy to think about. The mass of the pendulum. So if I took, a rope and attached a baseball to it, and then I took a rope and attached a basketball to it, and I let them both go, they would move with the same period. Isn't that amazing to think about?
It's the same.
What about a whale?
You take a whale on obviously a really strong cord, and you take a baseball, they would move with the same period. And there's a video so MIT does this thing called like online physics courses, and it's really crazy physics, and I've been watching a few of them. But it's all calculus involved. And this teacher actually gets enough money, and colleges have a ton of money so they can buy all this ridiculous stuff. He gets a pendulum that's like literally as tall as the ceiling with this big cord from it. And he actually gets on the pendulum. So first there's this big metal ball on the pendulum, and it's going back and forth. Then he sits on it and measures it, and they get the same exact period to prove that even if the mass changes, the period does not change. There's no mass in this period. Okay? And it's really interesting to think about. The reason is gravity, G, is the thing that's really keeping the pendulum in motion. That's what's affecting the G. Now, one second. The other thing is the length. And think about this for a second. Take a rope, and this is part of your lab, so I'm not going to give it away, or we're not going to do it yet. But you take a little rope like this long, okay? You raise up the bob, now we call this the bob of the pendulum, and you let it go. It's going to go like this, right? Follow me? Now, take a rope this long and let it go. What's it going to do? See the difference? Okay, this one is going to go through a much longer period than this one is. So as L increases, it is again in the numerator, just like the mass was before here. As the length increases, the period increases. So a longer rope means a longer period, which is logical. This part is the tougher part, because we have a constant G on Earth. But if you go to a different planet, the period of a pendulum would change based on the gravitational constant.
Wait, as the length increases, the what?
The period increases also.
Have they ever tried that? Like on a different planet?
Yeah, they did, Helen.
Maybe on the moon. The moon is 1/6.
Oh, maybe they did.
The moon is 1/6 G, so the period of a pendulum on the moon would be 6. The square root of 6. Square root of 6.
Would it
Because it's done to the right.
would it even move though on the moon?
Yeah. There's gravity on the moon.
No, I know, but I don't know.
It's just a smaller force of gravity. There is no.
Wait.
Hold on. You had a hand up first. Hold on. Tom.
Oh, how
You had a hand up the whole time. You just talking.
How come? Do you need an object on the end of a string, or can it go without?
No. If the string itself has mass, if it's a rod, a metal rod swinging back and forth, like ever seen like I know this is gross. Sorry, it's a plunger. Okay? But even without this mass on the end, even without.
Freshman year, wait, can I just tell you a little tidbit? It's so funny.
Yeah, I know. We have 1 minute. Go.
Okay, freshman year, that plunger was in this cabinet, and I took it out, and I was playing with it right before Father's Day theology class, and Caroline was sitting right here.
In a white shirt.
Oh no, you didn't.
A white shirt.
I went like this, just pretend to hit her, and just all this juice just expelled all over Caroline. Caroline's shirt was so.
It was I was soaked and it was see-through.
That's it.
And Mikey posed
And there was
as
food
a
all
lie.
over, and Posey was looking in the window. Posey was like,
Anyway,
ew.
so
Caroline, I forgot about that.
now we're good.
That was the foggiest thing ever.
Last thing, even without this weight though here, this has enough mass that it would do that. Okay, it would do that. Tonight, please. Tonight there's some, because we still have to do a bunch of examples on Friday, but I want you to work on something. So I'll put a few of those problems up tonight, not all of them. Have a good day. Now, what we have here again is a mass of 20 kilograms, a spring constant of 35. It's in simple harmonic motion, which tells us that we can use our period formula from the other day. Okay, somebody raise their hand, please. Tell me what we got for the period formula from the other day. Erica? Erica?
I don't know what that means. And then it's is equal to 2 pi, then the square root of m over k.
That's m over k, very good. M over k, perfect. Because we have, again, why is it m over k? Because we have a mass spring system. Okay, a mass spring system. If it was a pendulum, we would use L over G here. We'd use L over G. And
would you say tau equals 2 pi?
yes, and it's tau is the term. Yep, tau. Okay, T-A-U. Tau, T-A-U. Tau means period. That's that T-looking symbol. Okay? Now, what does it ask us to find? It says determine the period and the frequency. So let's find the period first by just plugging in what we know. It's already solved for. We don't have to do anything. So go ahead in your calculator, please. Type in 20 over 35. Take the square root and then multiply that answer by 2 pi. Okay? I would always do the radicand first. This is the way I've done it. But you can do it all in one line. As long as you use parentheses correctly. So in the calculator, 2 pi, and then press square root. It'll open a parentheses. Do 20 divided by 35. Close it. Hit enter. Give me 1 sec, Erica.
Wait, sorry.
Okay? What do you got for your period length, Erica?
4.75.
Units? It's measuring time.
Seconds.
Thank you. Okay. Remember, 4.75 when you round it. Now, you're measuring the time it takes for a wave to complete a cycle. So you're measuring time, therefore you remember seconds. If you don't remember that, look at this tau. It looks like T for time. Okay, think about it that way also.
Oh, so tau's always going to be time?
Tau is the time it takes for one complete cycle.
Period time. Oh,
Yes.
got it.
Okay?
Is that why it's like different periods in the day? Like in
Yeah, that's why the term, and even in hockey, they're not called quarters because there's 3 of them. You call them first period, second period, third period. They're periods of time. Tau is spelled T-A-U,
T-A-U?
which is different from T-A-O. Whose calculator is it? So ask instead of grabbing.
Now she got it.
I did that.
Now, next. We also want, stop guys, stop talking, let's go. We also want the frequency. Emmett.
W equals
1
over tau.
Good. Omega equals 1 over tau.
Omega.
Remember the terms, please. We're going to use those words. Omega, the frequency, there's omega-3 oils and stuff, yes. Equals 1 over tau. The other class, for some reason, saw this as an L. The other day, the other class thought this was L. It's 1. Okay, make sure we know that's a 1, not an L.
W is frequency.
Omega is frequency, not W. There's no W anywhere.
Brighter section, so.
Okay? Now, this just means 1 over 4.75. But everybody, look at your calculator right now. And instead of pressing 1 over 4.75, press 4.75. Then press x to the negative 1. It's above x squared. It's above x squared. And then hit enter.
Same answer.
Okay? Again, everybody press this, please. 4.75. Then look above x squared. You're going to see a symbol that says x to the negative 1. That means do the inverse, or 1 over. Hit enter. You should get 0.211. Okay? It's the same thing. I'm just trying to give you a command. That's it. So once you get your answer of 4.75, just press x to the negative 1. It'll do it for you.
Wait, 4.75.
Okay, x to the negative 1. You don't have that same calculator. You got to find it now. I don't know where it is on there. That's why I recommend it. It's okay. You'll find it. It's got to be on here somewhere.
I found this in like the locker.
I'm sure it's somewhere, right? So we're looking for x to the negative 1 or an inverse key somewhere.
I always think it's like that one, but it's not.
It's not. So you can just do this. Caret negative 1.
Did it to Mr. Hanley.
Okay.
Do which one? This one?
The carets raised it to a power. So 4.75 power negative 1, like that. Enter. Well, there you go. You learned something new. Units are Hertz. Frequency is Hertz. Next example. Determine. I know, you are. You gotta listen. I was talking about it for the last minute. Determine the length needed for a simple pendulum to have a frequency of 2 Hertz. Okay, different kind of problem. Now we have a pendulum, so we have a different formula. List your one given, because there's only one given here. Figure out the equation we're probably going to use to find L, or the length. And then think about what we have and what we have to do. You're welcome. So that's all we've got right now. That's it. There's literally one given here. But we do know the formula for period at least. Okay, because period involves L in it. Remember, the formula for the period of a pendulum is that 2 pi root L over G. So we know this. Okay, that's what we know. And we have this. And we are trying to figure out the length needed. We're trying to solve for this L right here. That's why we put this formula up. But there's a problem right away. The problem is this. We know G, 9.81. We know 2 pi.
How do we know we're on
Okay?
Earth?
But we don't know this right here. Okay? How do we know what?
No, we're on Earth.
Sorry. On Earth, determine. Thank you. That's a good point. If it's never stated, you assume you're on Earth. Okay? Because now we're looking at a pendulum and not a spring and a mass. Last time with the spring and a mass, we used the M and the K, but a pendulum is L over G. We're trying to find the length, so we're looking for L. We know G. We know 2 pi. We don't know tau, though. We don't know tau. Okay? But what was your other equation we had? Tau equals what? Or omega equals what? Yeah. The other equation we had was this. Omega equals 1 over tau. Remember that?
Yeah.
Everybody remember that one?
The one we just did.
The one we just did a second ago? Yeah.
So it's 2.
So what can we do?
Substitute.
Yeah, we can move things around, right? Solve for tau up here. If you solve for tau up here and plug it in down here, it'll work. Okay? So watch. Flip-flop these spots. And we can do this. We learned that with V equals X over T. So solve for tau up here. Take this expression that represents tau and plug it in over there. Because now we can use that because we were given omega in the beginning. And if we write this as 1 over omega, now we know everything in the equation except for L.
How are you able to just switch T and W?
Just the same way we can switch V and T. Multiply both sides by tau. Cancel, cancel. Leaving with 1 equals tau omega. Divide by omega on both sides. Cancel, cancel. You get tau equals 1 over omega. Okay? We got to know this, guys. You can always switch diagonally. Always. V equals X over T. We did that earlier this year. It's the same thing. So it's 1 over omega, which is, yes, 1/2, Erica. 1 over omega equals 2 pi root L over G. But what I'd like to do is solve for this algebraically. Okay? So let's go ahead and do that. How do I get rid of the 2 pi? Because I want to get L by itself. Helen? Very good. Watch what I'm going to write it as. Okay? So I put the 1 over 2 pi omega now. Because what are we doing? As Helen said, we're dividing by 2 pi, which simply means to move it down to the other side. Okay? Then I want to get rid of that square around the LG. Nicole, what do I do to get rid of a square? Root, sorry. What do I do to get rid of a square root? Say again? But I said it backward. What do I do to get rid of a square root? You square it, yeah. I apologize. I said that backward the first time. So square it, please. Square. What happens when you square a square root?
It disappears.
Leaving behind L over G. It's like magic, right? It's like magic.
You multiply by
I'm borrowing your line, sorry. So you square both sides. The square here and this square root cancel, leaving behind L over G. Continue. What do you want to get? What's the goal? What are we solving for, Emmett?
You want the L on its own, so you multiply its side by G.
Good. You want L by itself. Focus back there. You want L by itself. So we multiply both sides by G, as Emmett said. So pretty much bring the G out in front over here. Okay, multiply this G on both sides, so bring it over here pretty much. So we're going to end up getting G, parentheses 1 over 2 pi omega squared equals L. Okay? If you want to plug numbers in the beginning, please go ahead. But I know that some of you are doing this and are able to just keep up with this. Okay, it's up to you to choose. You want to solve algebraically like this? I would recommend it, because now your answer is correct no matter what. All you got to do is plug in numbers. But if you plug in numbers in the beginning, there is more room for error, I think. But again, it's up to you to pick your own, route. Helen.
It's 0.06.
Okay, let's go over this actually, because there's a common mistake people were making in the other class. You're right, Helen. It is 0.06. You did it right. But I want to emphasize something. Yes. 9.81.
Not negative.
No, that's only with free fall, remember? Relax. Now, here is the key. Everybody look up. When you type this in your calculator, the key to making this problem correct. I knew you were going to say that. The key to having this problem right. Listen. Come on, people. You need to do this. Thank you, Erica. You need to put your denominator in parentheses, because, again, listen carefully. If you type in the calculator 1 over 2 pi times 2, it's going to do 1 over 2 and then multiply by pi times 2. You need to think of this as one entity. Okay, you could write this as 4 pi if you would like. And I would recommend that. Just put 4 pi in the calculator. Because 2 times 2 is 4, and it's 4 pi. Okay? So 1 over 4 pi, but put the 4 pi in parentheses, square that term, hit enter, multiply by 9.81. Nicole.
I have another calculator question. You know
Okay.
how you have the key pi on calculator?
Uh-huh.
Would you use that? Or
Yes.
1.14?
I would use the key pi and just literally write 4 pi. You don't even need a time symbol. It knows it's there. You can literally press 4 second pi, which is second exponent, the little caret. That's where the pi is.
Why do you write 1 over 2? It's so much easier just to think of it as 0.5. Then you have no vision. Inside the parentheses.
Sure, you can do it as 0.5, but then it's 0.5 over 2 pi. Same difference, Helen. Same difference. Let's take a look at this. This would be 6.2 centimeters to make it realistic. Okay? What does 0.062 really mean to us, right? So, we're looking at a pendulum with a length of about 6.2 centimeters, so it's a very short pendulum. Okay? And on our lab on Monday, we're going to use something where the pendulum lengths are around 30 centimeters and 15 centimeters. So on the order of these numbers. Emmett.
Will we have to change it to 6.2 centimeters?
No. But if I said, express your answer in centimeters so we have a realistic approach, something like that, maybe. But I want you to see that what it is. But either answer is acceptable.
There's no way I'm doing that.
It's like right there. Go ahead. If the length of a simple pendulum is increased by a factor of 4, what happens to the period of oscillations? We're going to probably use that same formula. Let's write it down first, though. So here's what we've got.
I love you. Thank you.
We've got a length of some sort of pendulum. Okay, L. Doesn't matter. Modeling, relax. The other...
Why are you in a dog by yourself?
Here's our scenario.
You literally sound like a dog.
I don't want to know. The first pendulum has length L. the new pendulum.
Warm up to us.
Stop. Take a deep breath and stop talking.
Get some water.
I know you have so much time later to yell, but you know what? At the end of the day, when you're late for the pep ride, they're going to ask why, and I'm going to say, well, we couldn't finish physics because Helen was yelling.
Girl got a vuvuzela.
Now,
English?
so,
I get taken away from here. They're like, sorry.
what we're looking at,
You guys are so obnoxiously loud.
girls,
Oh my God,
stop.
2 seconds. We'll be done.
It's really annoying. Do you really want to get jug on a day like today? This is not cool at all. Okay? So don't get a second one. That's what we're saying. All right, Emmett, tell us what we can do with this kind of a problem. It's a pendulum.
I guess we just write out the equation for
Yes, exactly. We want to know what happens to the period. Let's write out the period equation here for this one. Okay? Then over here, we'll write this.
4 next to that.
Very good, Emmett. Very good.
And then you can conclude that it's 4 times as long.
Be careful. That's the misconception there.
So before L?
Okay, so let's go over this now. The answer's not for him, and that's the common mistake. Let me explain why. So here's what we have going on. Look, old pendulum, new pendulum. Look at the difference in the period. Emmett made a good statement and said replace L with 4L, because that's what's happening. It's 4 times as long, the new pendulum. Now, think about your arithmetic here. Break up the 4L into 2 separate radicals. Watch this.
Does this happen every single time?
2L over G and 2L over G.
4 times L over G. Make it like that. So take the 4 out in its own radical. Remember your laws of radicals. If you were to multiply this 4 times this L over G, you'd get back up here to 4L over G. Helen, what's the square root of 4? 2. Yeah, so in the end... Shh. Yes, but relax for a sec, guys. You're all yelling at once. You can't even hear each other. So as we said here, this becomes a 2. Now, I'll ask, and you can respond by raising your hand first. What happens to the period? What do you notice is the only difference now between the old period of the old pendulum and the new period now? Helen, what's the difference?
By a factor of 2.
A factor of 2. This is the only difference right here. Look at the formula. This is identical. This is the only 2 that's added on in a sense, but as a multiple, as a multiplier rather. So really, this is really, if you think about it, 4 pi root L over G. And if you compare these two, you'll see that this here is 4 pi, this is 2 pi, so this one is double this one. So what has happened to the period? The period has doubled. Now, before we go any further, listen carefully. We know it's doubled because it was the square root of 4, Chaz. If we didn't use 4 and we had used 9, Chaz, what would happen if we didn't use 4 and we used 9? What would be the difference here? So this is 9 now, Chaz, which makes this 9. So what's this going to be? No?
Who's answering this question?
Chaz is answering this question. Yeah. Come on, stop. I emphasized like 8 times so the 2 of you wouldn't call an answer.
Yes, we know. That's why we're
Obviously.
all the time.
Go ahead.
You know what? I feel simple now.
Go ahead, Chaz.
Chaz's question.
You'll be multiplying by 9 instead of 4.
Good, so this becomes,
That would be 18, right?
be careful, this is a 9, which makes square root of 9 equal to,
Sorry, 3 and 6.
yeah.
Thank you.
So, again, let's go over this. If this had been a 9, watch, I'm going to write over it in red.
Why would it be 9?
Hypothetically speaking, listen to the question, please. Okay, it's not really 9, Sybil. I'm saying in another problem, had it been 9. Okay, watch what would have happened. Okay, which would make this 6. Now, what you're noticing, why is that absurd, Sybil? I'm confused what you're asking right now. This is a new problem. Make believe instead of the problem saying it was 4 times as long, now it says 9. What you get is 3 here. Okay, which makes this 6. So, what we notice is now this is triple the period. So it's simply the square root of whatever the length went up by. If the length went up by 16, the period would go up by 4. If the length went up by 25, the period would go up by 5. Okay? Okay? Again, hold on. I see your hand, Nicole. Okay, so it's going up by the square root. You want to make the statement, or is that what you're going to say, or can I make it real quick before you have a question? So, write this down, people, write this down, let's go. If the length of the pendulum increases, write faster, let's go. If the length of a pendulum increases by a given factor, and call that factor capital D, for example. Some factor, we don't know what it is. So again, if the length of a pendulum increases by a given factor D, then the period goes up by, or increases by, the square root of D. This is how we learn real physics, how we generalize. That SAT 2 in physics, these are the kind of questions they're going to ask you. They'll give you a formula, say, here's the formula for the period of a pendulum. If the length of the pendulum increases by 36, what happens to the period? Well, it goes up by 6, because the L in the original equation is under the radical. So by default, if this goes up by some number, say the number is 50, then the period goes up by the square root of 50, which is approximately 7.05 or something. Okay? So any number that L goes up by, the period's going to go up by the square root of that, because L was originally under the square root in the equation. So you'd have to take the square root of whatever that increased factor is.
All right, let's get to
Nicole.
the next.
Guys, stop!
So technically, it's always going to be like a perfect square because it's going to be the other number.
It could. But again, if it went up by a factor of 50, sure, it's a decimal. Helen. You know? Raise your hand.
I said rumpus time is over.
The last one here. It's going to take you a minute to write it down. Please write it down carefully. This is the kind of question you expect for free response. This is the kind of question you could expect. The mathematical question. Because it makes it a little bit tricky. Okay? A mattress, I'll dictate. A mattress is really a surface that rests on a multitude of springs, on many springs. Now, I know Tempur-Pedics are not springs in that. Yes, I know you were going to say it. But anything with elasticity can be modeled as a spring. So you can mentally think about it as a bunch of springs, even though it's not. But old school mattresses were a bunch of springs in a matrix or in some sort of row column arrangement. So again, a mattress is really a surface that rests on a multitude of springs. Imagine that there are 20 springs inside of a mattress. So imagine there are 20 springs. So you might have a 4x5 arrangement of springs. So it would look like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So those are all the springs from a bird's eye view. There are 20 springs, and the mattress is on top of this, or the springs are inside of the mattress like that. So you're looking down on the mattress right now. If the bed has a mass of 10 kilograms, and a person lying on it has a mass of 60 kilograms, yeah, the bed is always less than the person. If you think about it, pick up a mattress, they're not heavy. They don't weigh as much as a person weighs, okay?
All right, muscle man.
They really don't though, okay? Now, determine the spring constant of a single spring. That's the key there. Underline single. Of a single spring, because a lot of people make mistakes on this, because they think about all the springs. Of a single spring, if the simple harmonic vibration, which just means the spring's vibrating, okay? If the simple harmonic vibration, and in parentheses you're going to see immediately after the person lies down. So it's going to damper out. You lay on a bed, it's going to vibrate for a second, right? It's going to kind of, you'll feel that, but it'll stop. But imagine immediately when you lay on it, it's going to have some oscillation. So we're told that the period is 8 seconds. Okay? And we want to find K of one spring.
I don't have any.
We want to find K of one spring.
I know I owe you a pen, and I have it in my locker somewhere. I'll give it back to you, I promise.
Now, spring mass system right away, because we have a mass, we have a spring. What is the mass that's acting on this bed, or overall that's acting on the springs, I should say?
Would be the person.
Person?
Person and force of gravity.
Well, the force of gravity for sure.
What about the other mass?
But we have to think about the mass of the bed itself. Now, we know that all the mass is not on top of the springs. Some is below it. For the sake of simplicity, we'll just say it's the sum of the masses. But technically, I would probably use 65 as a number, because say half the mass is on top of the bed. But let's imagine, because we're modeling, that it really looks like this.
70.
Imagine that it's like a plank on top of 20 springs. Oops, I should spread them out a little bit more if there's 20. Because we're going to think about this as going deep 4. Okay, so 1, 2, 3, 4, 5 springs, and they go back 4 deep, okay? So this is like a side view of the bed. I know a mattress does not look like this, but this is how we're modeling it. So the overall mass is going to be 70 of this object and the person together, pushing down on these 20 springs. But how many springs? 20 springs. 20. The 60 from the person and the 10 from the bed. We're thinking of the bed as if it's a plank on top of springs. Okay?
Wait, so do we
Yeah.
divide the 70 by 20?
That's what we're going to figure out. Let's look at our formula. We have to look at our formula. That's one way to think about it, Helen. One way to think about it is that, but there's another way to do it. It might be easier. Think about the formula. Tau equals 2 pi root m over k. Now,
Wait, could you scroll up for 2 seconds? Sorry.
for this kind of a problem here,
I just want to see that thing. Oh, thank you.
okay, for this kind of a problem, how many springs do we have?
20.
20. We have 20 springs. So there's 20 k values here, aren't there?
Yeah.
So instead of putting k, we simply put 20k. Or we can solve for this k and then divide by 20 in the end. Because the k, this k right here, we call this KEQ actually in physics or in engineering, KEQ, which means the equivalent spring, as if there were one big spring. So if you solve this equation for k, you need to divide by 20 because there's 20 springs that they're being displaced on. Or you can simply just put a 20 in front of here and make it 20k. Either way. So either put a 20k here and in the end solve for k, or solve for k by itself like it is now and divide by 20. But it's the same thing. Helen, what you said also works. Okay? You said divide the mass by 20.
I don't like doing so.
No, but you said divide the mass by 20, right? That's like putting a 20 here. Take the mass, dividing it by 20 is putting a 20 here. That's what I just said. It's the same thing.
So at the end I can just divide the k by 20.
Yes, you can
Or
divide.
can I just start dividing the mass by 20?
Yep, either way works. But not both, Helen. Not both.
Yeah.
Go ahead.
Wouldn't
Sorry, Steph.
multiplying 20 and k together and keeping it under there, and then just like solving for k and then dividing?
It's the same thing as dividing by 20.
Wouldn't it be the opposite then?
No, because watch. When you solve for k, you're going to move it up here. Right? Eventually, you're going to move it up out of the
Because you're gonna
denominator.
multiply
And then you're going to divide by that 20 anyway at the end. Because there's going to be a 20 coefficient in front of it.
So why can't we just leave it at k?
We're going to. I'm saying we can do it either way. We can do it either
would
way.
just be like extra work.
Yeah, it doesn't matter. Well, it's not even extra work. It's just it's up to your preference. Okay?
Third or whatever.
Let's solve for k. Get rid of the 2 pi, everybody.
Wait, why did you get rid of... Oh.
We're solving for k.
Everybody.
This is quite tricky, by the way. This process, so stay with me,
rhyming.
please.
Seriously.
Square both sides. Remember, when you put this in your calculator, to put the 2 pi in parentheses. Bless you. Because it's a quantity and it's in a denominator. You want it to divide by the whole denominator, which is all 2 pi. Okay? How do I do this now, Emmett? What should I do next? Because this is where people get tricked up. Shh. Say again?
Multiply by 1 over m.
Okay, but that's going to leave KQ in the denominator, though. Right? Erica.
You switch k with tau over 2 pi.
Yeah. Take this entire thing and this entire thing and flip-flop. Think of it as v equals x over t again. This is like velocity equals displacement over time. You could flip-flop the V and the T. Just do the same thing to get K up top.
Wait, why can you do that?
Why can't you or why can you?
Why do you need to do that?
Because you're trying to find K. And if you divide by M, it gets rid of the M, but it leaves this as 1 over K. You see that? But you want K, not 1 over K. So just flip-flop, makes it easier.
But isn't it like we have two denominators?
Yeah, it's not a big deal though. So what I would just do is this, guys. Just take this value, determine it, and then divide it into 70. Okay, so take 70 and divide it by, what was the period, 8 seconds?
Yeah.
So 8 over 2 pi. Do that first. And what does 8 over 2 reduce to?
What's 7?
Yeah,
70.
4 pi.
70 is the mass. The bed was 10 and the person was 60.
4 pi up to.
Not 4 pi, 4 over pi.
I don't do that.
Okay? It's 4 over pi now when they cancel. Okay, squared. And divide that into 70. Helen, what do you get for this when you do it?
I got 2.17. I don't know if that's.
That's the answer after you divide by 20 though. I'm asking for this answer.
Oh, I don't know. I didn't do it that way. I don't know. I didn't do that.
Erica? There it is. Guys, hold on. 1 minute, not even. This is the equivalent spring as if there was one spring. But how many are there?
20.
So Helen, what do you get for one individual?
7.
Tom is ready home to go to the receiver.
Your homework, listen, is on Moodle. Your problem set is on Moodle. I would really like your problem sets for Wednesday. Because the test is on Thursday. So you can come in with questions. Listen. So you can come in for questions on Wednesday during your review. One last thing to listen to. Heed my advice here. On Monday, you guys have a lab. The other group had their lab yesterday. So they're getting a head start working on it this weekend. So you should make sure you work on the problem set this weekend. So next week, when we do the lab on Monday, you can work on that at night on Monday and Tuesday. Because they're going to be working on the problem set next week on Monday and Tuesday. You work on it this weekend.
How many problems are in the problem?
About 32. Looks like around 32.